Decoding Quantum Algorithms, a deep dive into tomorrow's computing power in an era defined by exponential growth in computational demands. Quantum algorithms stand out as revolutionary tools capable of solving problems deemed impossible for classical computers. By leveraging principles of quantum mechanics such as superposition and entanglement, these algorithms redefine the boundaries of computation. This exploration delves into the architecture, functionality, and implications of quantum algorithms. From foundational theories to real-world applications, we'll uncover how these innovations could reshape fields ranging from cryptography to artificial intelligence. The foundations of quantum algorithms. At the heart of quantum computing lies the qubit, a fundamental unit that differs drastically from classical bits. While traditional bits exist in states of either 0 or 1, qubits leverage superposition to represent both simultaneously. This property allows quantum algorithms to process vast amounts of information in parallel. Entanglement further amplifies the power of quantum systems. When qubits become entangled, the state of one instantaneously influences another, regardless of distance. This phenomenon enables complex computations through interconnected operations that classical systems cannot replicate. These principles form the basis for designing quantum algorithms. Unlike classical counterparts, which rely on deterministic logic gates, quantum algorithms utilize probabilistic operations governed by quantum amplitudes. This shift introduces new paradigms in problem-solving approaches. For example, Shor's algorithm leverages number theory combined with quantum Fourier transforms to factorize integers exponentially faster than known classical methods. Such capabilities challenge existing cryptographic frameworks and highlight the disruptive potential of quantum computing. Superposition enables simultaneous processing of multiple inputs, enhancing efficiency for tasks requiring combinatorial analysis. Entanglement creates correlations between qubits, allowing distributed computations that defy classical limitations. Interference manipulates probabilities within quantum states to amplify correct solutions while canceling out incorrect ones. Quantum speedup and algorithmic paradigms. Quantum speedup refers to the ability of certain algorithms to solve problems significantly faster than their classical equivalents. This advantage stems from exploiting quantum properties rather than relying solely on hardware improvements. Grover's search algorithm exemplifies this concept by providing quadratic speedup for unstructured database searches. Instead of checking entries sequentially, it utilizes amplitude amplification to locate target items in fewer iterations. Such breakthroughs necessitate rethinking algorithm design. Traditional complexity classes like P and NP may require revision when considering quantum capabilities, leading to the emergence of new classifications such as BQP, bounded error quantum polynomial time. BQP encompasses decision problems solvable efficiently by quantum computers but not necessarily by classical machines. Problems related to factoring, discrete logarithms, and simulating quantum systems fall squarely within this category. Comparative analysis of quantum versus classical complexity. Classical algorithms often exhibit polynomial or exponential runtime dependencies, whereas many quantum algorithms achieve polylogarithmic or square root complexities. For instance, finding a needle in a haystack becomes feasible with O(n) queries instead of O(n). This disparity grows more pronounced with larger input sizes. Tasks involving massive datasets or high-dimensional spaces benefit disproportionately from quantum advantages due to inherent scalability features. However, not all problems yield substantial gains from quantum approaches. Those with structured patterns or already optimized classical solutions show minimal improvement, emphasizing the importance of identifying suitable application. Domains. Applications in cryptographic systems. Cryptography stands at the forefront of quantum algorithm impact. Current encryption standards like RSA and ECC depend on mathematical hardness assumptions vulnerable to quantum attacks via Shor's algorithm. Shor's algorithm exploits periodicity in modular exponentiation to rapidly factor large numbers, a task impractical for classical systems. Its execution requires only polynomial resources relative to the number of digits, rendering existing public key infrastructures obsolete. To counteract these threats, post-quantum cryptography initiatives explore lattice-based, hash-based, and multivariate polynomial schemes resistant to quantum decryption attempts. These alternatives aim to preserve security until quantum-resistant protocols gain widespread adoption. Meanwhile, Grover's algorithm poses challenges for symmetric encryption. Although doubling key lengths mitigates its effect, ongoing research seeks robust solutions ensuring resilience against brute force attacks accelerated by quantum processing. Design challenges and implementation hurdles. Developing functional quantum algorithms faces formidable obstacles. Qubit coherence times remain limited, restricting the duration over which quantum states maintain stability during computations. Noise introduced by environmental interactions degrades qubit fidelity, necessitating error correction techniques that increase resource overhead. Surface code implementations demand thousands of physical qubits to simulate single logical qubits reliably. Scalability presents another significant barrier. Maintaining low error rates across growing qubit counts remains elusive despite advancements in superconducting circuits, trapped ions, and photonic platforms. Fault tolerance mechanisms add layers of complexity, requiring precise control over quantum operations while managing decoherence effects. Balancing performance with practical constraints defines current research priorities. Evolving hardware requirements. Early-stage prototypes operate with handfuls of qubits, insufficient for executing meaningful algorithms beyond theoretical demonstrations. Achieving fault-tolerant universal quantum computing likely demands millions of physical qubits in the coming decades. Current architectures struggle to meet stringent connectivity requirements demanded by algorithmic designs. Topological qubits offer promise through reduced susceptibility to noise but remain experimental outside controlled lab environments. Optimizing gate operations and minimizing crosstalk between qubits constitute active areas of investigation. Innovations in materials science and nanofabrication hold potential for overcoming present-day limitations. Quantum machine learning and optimization. Machine learning benefits immensely from quantum enhancements. Quantum support vector machines, QSVMs, demonstrate improved kernel evaluation speeds, accelerating pattern recognition processes. Hybrid models combining classical pre-processing with quantum feature mapping enable tackling higher dimensional data sets previously intractable for conventional neural networks. Quantum annealing provides novel optimization pathways for combinatorial problems. D-Wave systems showcase adiabatic quantum computing applied to logistics, finance, and material discovery contexts. Despite promising results, integration hurdles persist. Mapping machine learning tasks onto quantum hardware often incurs overhead losses, negating expected gains unless specialized circuitry evolves accordingly. Future directions and research frontiers. Ongoing efforts focus on refining variational quantum eigensolvers, VQE, for chemistry simulations and developing efficient quantum random access memory, QRAM, structures. Topological quantum computing offers alternative routes towards stable qubits through non-abelian ennions, though realizing scalable devices remains technically demanding. Advancements in quantum classical hybrid algorithms continue to expand applicability domains, bridging gaps between abstract, theoretical constructs and tangible implementations. Collaborative projects spanning academia, industry, and government agencies drive innovation forward, addressing cross-cutting challenges in software development, hardware engineering, and algorithmic theory. Conclusion: quantum algorithms represent a paradigm shift in computational methodology, unlocking unprecedented opportunities across diverse disciplines. Their development hinges on resolving intricate technical challenges while fostering interdisciplinary collaboration. As researchers push boundaries in both theoretical foundations and practical implementations, staying informed about emerging trends ensures readiness for upcoming technological revolutions reshaping our digital landscape.